Good evening, everyone. So we'll now proceed to the volume of the solids. I will discuss volume of solids, which is in general form. So we'll have the volume of solids that are in upright position, such as, for example, the cylinder, prism, and any other solid whose cross-section is uniform across the length of the solid, such as, for example, this solid of extrusion. To compute the volume of this solid, our formula is only to compute the area of the base, multiply it by the height. Assuming the height of the solids is h, then we can compute the volume of the solids using this formula. Area of the base times the height of the solid. Okay, assuming that the height of the solid is slanted, what I mean is, for example, we have the cylinder in this orientation, or we may have the prism in that same orientation. How do we compute the volume of that solid? If the height of the solid is the same h, and the cross-sectional area is still the same area of the base, then we may compute the volume of the solid using the same formula. The area of the base times the height of the solid. The height of the solid for the oblique solids in this case refers to the vertical height. Now, why did the formula did not change? Let us consider a stack of coins here. Supposing we have this stack of coins and we rearrange this stack of coins in this form. As you may observe, the coins has landed in the orientation, but the quantity of coins is the same. It follows that the volume of the coins is still the same. The height after slanting the stack is still the same, say h. So it means regardless of the orientation of the solid, as long as the cross-sectional area of the solid is still the same, the volume will be the same. We may also compute the solid or the volume of this oblique solid using another formula. Let us consider this side view of these oblique solids. So let's say this is the view of this oblique solid. If we cut this in this position perpendicular to the element of the solid, this is perpendicular, then this may generate an area which we call as the AC, which means an area along the cross-section of the solid perpendicular to its element. Now, if we remove this area and we place it on the other side of the solid, what we get is an upright solid. An upright solid with a height equivalent to the slant height of the solid, so let's say L. So meaning we may now calculate the volume of these oblique solids using the same formula as that of the upright solids. Our formula will then be area of the cross section of the base, which is in this case is AC, times the slant or the height of the solid, which is L. So we may also include another formula to compute the volume of the solid to be equal to the area of the cross section times the length of the solid. So the cross section of the solid now appears different as compared to the original base area in this case. In the case of the oblique cylinder, we have here an ellipse. Here, it is also an ellipse but of different form. For the oblique prism, we also have different area now. Okay, let's proceed. So this say is the slant height of the solid. The slant height of the solid is the length of the element that generates the lateral area of the solid. Like for example, in the case of the cylinder, this is its slant height or the length of its element. Okay, how about computing the lateral area of this solid? Okay, we have formula for the upright solids. In the case of the cylinder, the prism, or any other solid of extrusion, the formula to calculate the lateral area is simple. Let us consider this cylinder. We cut the cylinder along that length, for example. If we cut the cylinder along that length and then we unfold that cylinder, what we get is this surface. If we make the surface plane, then we'll have a rectangle. As you may observe, the height of this rectangle is the height of our cylinder. The length of this one, the length of this area is equal to this length of this cylinder, which is the length of the circumference of the cylinder. I will call the circumference of the cylinder as the perimeter of its circumference, PB. In the case of cylinder, the circumference or the perimeter of the base is simply its circumference. This is also true for the rest of these solids, as long as the cross-sectional area is the same. So we may calculate the lateral area to be equal to the circumference or the perimeter of the base times the height of the solid. Okay, for other solids, we may also do the same by cutting the element or by cutting the lateral area in that direction parallel to the length of the solid. And then we unfold that area and then we compute the area that is generated by the unfolding. Now, what will happen if these solids, okay, what will happen if these solids are oriented in an angle? Say we have an oblique solids. How do we compute this lateral area now? By the way, the lateral area is the area that is on the side of the solid. It does not include the area on top or at the bottom of the solid. If we include the area on the top and at the bottom of the solid, then it now uh, called the total surface area. But for the lateral area, we'll only consider the area that is generated by the element of the solid. In the case of the oblique solids, we might be tempted to use the same formula as of the solid, volume of the solid, perimeter of the base times the height, or we may also tempted to use this formula, thus the perimeter of the cross-section times the length of the oblique solid. As you may observe, this is analog to the volume of our solid. But in the case of the lateral area of the solid, this analog does not work anymore. So we will use another formula to compute for the lateral area of oblique solids of this form. And our formula is this one. We will compute the perimeter of the base. The base, in this case, is circular. This is rectangular. This is pentagonal. And this is a Malayang Hugis solid. So we may compute their perimeter and then multiply it by the slant height. Okay, so in the case of this solid of extrusion, how do we compute its perimeter? In this case, we will use a special device. The device is called planimeter. Planimeter is a device that is used to measure the area of an irregularly shaped solid. Okay, let us try this problem. The base of a circular cylinder is 12 centimeters squared and an element of the cylinder is 10 centimeters. Find the volume of the cylinder if the element is inclined to the base at an angle of 60 degrees. Here is our diagram. The base is 12. The length of the element is 10, which is the slant height, and the solid is inclined at an angle of 60 degrees. We are asked to compute the volume. Now we know that if we have a cross-sectional area, we need only to multiply it by the vertical height of that solid to compute the volume. Okay, the question is, what is the vertical height? We can compute the vertical height because we have the length of the slant height. This one is equal to 10. The angle is equal to 60 degrees. Now, the opposite side may be computed using the trigonometry formula, which is the sine formula. So we'll have the height will be equal to 10 sine of 60. So we now have the volume. The volume is the cross-sectional area of the base times the vertical height is equal to area of the base times height. So our volume is equal to 103.9. Okay, we have another form of volume of the solids in upright position. These solids, which we have illustrated earlier, the volume of solids of cylinder, prism, and other solid of extrusion may be have of this form. If we reduce the cross-sectional area of the base as we go along the length of the solid, will generate this area. In the case of the cylinder, this is a cone. In the case of the uh, prism, this is a pyramid. This is also a prism. We also have another pyramid. In the case of the solid of extrusion, the solid that is generated is in is we cannot or shall we call it that solid. Okay, now compute the volume of the solid. We'll use the same formula for the volume of our original solids, the area of the base times the height. But this volume is now obviously smaller compared to the original volume, and this is only a third of that original volume. How about for the oblique solids? Now, if this solid's vertical height or this solid's height is slanted, then we'll have this kind of solid. How do we compute their volume? Now, our volume, area of the base times height divided by 3 is still true. This is an analog of an original volume formula that the volume of the solid does not change whether we slant or whatever position we orient the axis of the solid. It is simply an rearrangement of the mass of the solid, but the volume is not affected. But we might be tempted to use the other formula because this is analog to our original formula. The cross-sectional area times the length divided by 3. Now, this is not true. Why? It is because we cannot define the cross-sectional area of our solid. In a case of our original cylinder, in a case of our original cylinder, we can define the cross-sectional area of the cylinder to be the same an ellipse. But if the solid is in oblique form, it may not be the same, or it may not have uniform cross-sectional area, uh, or the cross-sectional area all throughout the length of the solid is not uniform or not similar. Okay, So how about the lateral area of these solids? The lateral area of the solid is now somewhat different. In the case of the cone, the area is equal to pi r L, where r is the radius of the base and L is the slant height. In the case of the prism, we will simply calculate the area of its lateral faces, which is in this case are triangles. In the case of, in the case of another pyramid, the same, as you can see that the lateral faces are triangular. And in the case of solid of extrusion, we may not be able to compute the area using the formula. Okay, let us try this problem. Find the length of the diagonal of a cube of edge A. Here is our cube, and we are to find the length of the diagonal. Let's call this y. Now, we can determine the diagonal from the triangle. We have the vertical height of this cube to be equal to A. And we also have the diagonal of the base, which is that one. So we'll call this x. Now, what we have is a right triangle, where we can compute the value of y using the Pythagorean formula. What is given here is only the a, meaning x is not known, meaning we cannot determine y unless we do not know the value of x. So we need to first calculate the value of x. But the value of x may be determined from another right triangle, which is the base of this solid. Now, the x may be computed using the Pythagorean formula, and we have an x squared to be equal to this value. Since we now have the value of x squared, we may now proceed in determining the value of y. Using the same Pythagorean formula, we have a squared plus x squared. Extract its square root, then that will be our y. So our y is equal to a squared. And since our x squared is equal to 2a squared, then we'll have y to be equal to a square root of 3. Okay, let's try this another problem. Compute the weight of a piece of lumber 400 mm by 600 mm, 6 meter long if the lumber weighs 960 kilogram per cubic meter. Okay, this is our lumber. The dimensions are 0.6, 0.4, and 6. Let's now compute its volume. The volume is the length times width times height, and our volume is 1.44 cubic meter. And according to the problem, each cubic meter of this solid weighs 960. So how many 960 are in there? Since we have 1.44 cubic meters, then each of that cubic meter weighs 960 kilogram. Then our total mass is 1,382.4 kilograms. Okay, next. What is the altitude of parallelepiped? Oh, if the altitude of parallelepiped is 20 centimeter and the base is a rhombus with diagonals 10 and 16 centimeters respectively, find its volume. This is our solid. The height is 20. The diagonals are 10 and 16. Now, to compute the volume of this solid, we simply compute the cross-sectional area, multiply it by the altitude or the height. Now, how do we compute the height? To compute the area first, we'll compute the area since this solid is a rhombus. The area of the base or the rhombus may be computed using the diagonals. 1/2 of the smaller times the bigger diagonals, sine of the angle between them. In the case of the rhombus, the angle formed by the intersection of its diagonal is 90 degrees. That is why the sine of 90 degrees here is not visible because it is equal to 1. So we may now compute the area. Now to compute the volume, we multiply the area by the height of the solid. Then we'll have this volume. Okay, it doesn't matter whether this solid is oblique or upright. The volume is still the same. Next, the lateral area of a right prism is 162 square meter, and the base is a rectangle 3 by 6 meters. Find the altitude of the prism. Okay, here is our prism. The base has a dimension of 3 by 6, and we are going to find the altitude. What we are given is the total lateral area. Where are the lateral areas? One is this rectangle. This rectangle has an area of h by 3, which is this one. And since this area is also similar to the area at the back, then we multiply it by 2. Another area is this area, a length of 3, or a length of, okay, nabaliktad, no? This is supposed to be, this is the previous illustration must mean this area, this area. Now the other one is, assuming this is 6. So this is 6 times height, and it has a similar face on the other side, where is this one. So the total area, 6 times h and times 2. And the total lateral area is equal to 162. In this case, the only variable is h. Then we may compute the h using algebraic manipulation or using the shift-solve function of the calculator. Okay, now let's proceed. Find the volume of a regular square pyramid. If each edge of the base measures 10 inches and the slant height of the pyramid measures 13 inches. Here is our solid. It has a 10 by 10 base, is a square, and according to the problem, the slant height is 13. Okay, so the distance from the center of the pyramid to the midpoint of its side is equal to 5, which is half of the side of the pyramid. Now, we are familiar that the volume of the pyramid may be calculated using the area of the base times the vertical height of the solid, and then we divide it by 3. But the question is, what is our h? Our h may be computed from the Pythagorean formula. As we can see here, we have a right triangle, 13 being the hypotenuse and h being the height. So we can now compute the h using the Pythagorean formula, and we found out to be equal to 12. Now we will compute the area of the base. The area of the base is a square with dimension 10 by 10, so we'll have an area of 100. So computing for the volume of the solid, we'll have 400. Okay, let's now proceed to this kind of solid. Previously, we have the solid of, we have the cone. Now, if we cut the cone parallel to the base, what we get is called the frustum of the cone. Likewise, if we have a pyramid and we cut the pyramid perpendicular to the base, or if the cutting plane is parallel to the base, what we get is a frustum of the pyramid. How do we compute the volume of the solid? This is our formula to compute the volume of the solid. First, determine the area of the base in the height and substitute to these formulas. After computing the area of the upper and lower bases, we determine the vertical height of the solid, h, and then we divide it by 3, and then that will be the volume of our frustum of the solid. Now, to compute for the lateral area of the solids, take note class that this is a special solid. It must be in upright position. We restrict that in that condition. So the lateral area of the solid, we simply multiply the perimeter of the base area plus the perimeter of the upper base area, multiply it by the slant height of the solid times half. Okay, let's try this. The frustum of a regular triangular pyramid has an equilateral triangles of its base measuring 3 meters and 9 meters respectively. If the bases are 8 meters apart, determine its volume. This is our solid. This is triangular, a dimension of 9 on each side. Equilateral triangle. Equilateral means equal length triangles. The upper base is also an equilateral triangle. This means that the bases are similar shapes. So this is a frustum of a pyramid. So how do we compute the volume? We compute the volume using the formula we have stated earlier. The volume is equal to this formula. We have to compute the area of the base. But what is the base? The base is a triangular. We know that the area of the triangle given its base is in the included angle is 1/2. Okay, first the height is 8. Now compute the area of the base. The area of the base is 1/2 A B sine theta. The A is the leg and B is the other leg, and theta is the angle included between the two legs. In the case of our base here is a triangle. The length of the side is 90, the other side is 90, and the third side is also, I'm sorry, not 90 but 9. Now, this is an equilateral triangle, meaning equal lengths. It is also an equiangular. It means that the angle in each vertex is equal. Since the total angle of a triangle is 180, it means that each of these vertex must has an angle of 60 degrees. So that is why we have sine 60. Now, to compute for the area of the upper base, we have the same formula, 1/2 AB sine theta. And then compute the volume by substituting everything to our formula. Okay, let's now proceed. Find the volume of the frustum of a right circular cone whose slant height is 10 and whose radii are 3 and 9 centimeters. Okay, so this is our cone. The slant height is 10, the radius of the base is 9, and of the upper base is 3. So we compute the volume using the same formula for this frustum. We have to compute first the area of the lower base or the upper base in this case, pi r squared. So we have pi and the radius is equal to 3 and we have squared. For the second area, which is the lower base, pi, the radius is 9 squared. Now to compute for the height of the solid, the vertical height may be computed using Pythagorean formula. From the Pythagorean formula, or the side view of the solid, the vertical height is equal to h. In this case is here. We also have the hypotenuse in this case is 10. Now our concern is only this side. If we know the length of this segment, then we have a right triangle. We can compute the height using the Pythagorean formula. Okay, we know that the upper base is equal to 3, then the projection of the upper base is also equal to 3. Since this is a total of 9, meaning this is 3, and the remaining segments must be equal to 6. 6 divided by 2 is equal to 3, meaning this is 3, this is also 3. Now we have here a triangle. The hypotenuse is 10, the base is 3, the height is 3. Then we can use the Pythagorean formula to compute the h. 10 square, the hypotenuse, minus 1 of the side is 3 square. Then we have the height to be equal to square root of 91. Substituting everything to our formula, we'll get 372 pi as our volume. Okay, here we have another kind of prism, but it is cut in some unique way, such that each element of this prism forms different heights. So let's say h1, h2, h3, h4, and h5. Then how do we compute the volume? We know that the volume of the prism is simply the area of the base times the height of the solid. In this case, we have a defined area of the base, but the height, vertical height, is not defined because it has different lengths. Now we will use the same formula in this case. We'll use the area of the base times the equivalent height of the solid. The equivalent height of the solid is the average height of that length. We simply compute the average of that height, and then that will be our height. Then we can compute the volume of that solid. Now we have here another solid. This solid is called prismatoid. What is a prismatoid? By definition, a prismatoid is a solid which has a polygon basis. In this case, we have two bases, of course. The lower base is a polygon. The upper base is also a polygon. The upper is triangular. The lower base is an quadrilateral polygon. And these two bases is connected continuously by the other faces. Like for example, this one we have a triangle, this one is also a triangle, such that the faces or the lateral faces or the vertices of these lateral faces lie only on the two bases of this solid. If this qualification is satisfied or this definition is satisfied, then we can use the Prismoidal formula to calculate the volume of this solid. How to do that? To calculate the volume of the solid, first is to determine the distance between the two bases. So let's say it's h, and then we divide it by 6. And then we determine the area of the upper and of the lower bases. And then we go somewhere between, exactly halfway between the upper and the lower base, and let's define an area. In that case, is the cross-sectional area of this solid. If the area of that solid, or if the area of the cross-section is defined, then we may use that in the formula, which is in this case is A2. If this is area 1, and the middle is area 2, and this is area 3, then our formula is h over 6 upper base, lower base, 4 times the middle base area. Okay, a solid has a circular base diameter 20 centimeter. Find the volume of the solid if every cutting plane perpendicular to the base along a given diameter is an equilateral triangle. Okay, what is that solid? Here is that solid. As you can see, it seems to have a dome on the upper side of this area. But this is not a dome. According to the statement, if we cut this solid along the diameter, this is one of the diameter of the solid. If we cut this solid along one of its diameter, it will reveal an equilateral triangle. It follows therefore that if we cut this in that position, we'll have also the same equilateral triangle, but now of smaller size, until we get to the other end of the solid, wherein we have our equilateral triangle whose dimension is equal to 0 by 0 by 0, or an equilateral triangle which side is equal to 0 at the end point of the diameter. So, how do we compute the area of the solid? Now, let's try to see if this formula or if this solid qualifies the Prismatoid formula. First, it must have two bases. Yes, it does have two bases, polygonal bases. In the other side is an equilateral triangle which dimension is 0 by 0 by 0 on all of its sides. The same on the other side. We have also here an equilateral triangle with lengths or with legs equal to 0. And these two bases is connected by smooth face here. Then we may use the Prismoidal formula for the prismatoid. So here, determine the h, the area of the base 1 and the area of the base 3. Okay, our height is the distance between the two faces, the bases. The diameter is 20. And the area of the base here is 0, and on the other side is also 0. The middle area in this case is the maximum rectangle or the maximum equilateral triangle. An area may be calculated using this formula, 1/2 AB sine theta. Our A is 20. Okay, is that really 20? Let's try. Uh, okay, this is an equilateral triangle. Okay, the diameter of the circle is 20. Then, since this is 20 and this is an equilateral triangle, then the other sides must be also equal to 20. So, the A is 20, the B is 20. Since it is equilateral triangle, then each angle on the vertex is equal to 60. Why 60? It's because the total angle in a triangle is 180. And since there are three angles, then each angle must measure 60. So we have the volume equal to this value. Okay, here is our polyhedrons. Poly means many, hedrons mean phase. These are called the Platonic solids. There are only 5 known Platonic solids. And in fact, there will be only 5 Platonic solids. Platonic solids or regular solids. These solids are bounded by regular faces. This one is called the tetrahedron, meaning it has 4 faces. The face in this case are triangles. The area may be computed using the formula. Others, lectures ako. Lectures ako. And the volume is equal to this formula. Here we also have hexahedron. For the hexa, which means 6 and hedron faces, we have here cube. It is simply a cube. The area is 6 face. The face area is 6 face. We have also for octahedron. Octa, which means 8, hedron face. There are 8 faces in this case. The solid is composed of 2 pyramids. There are 8 triangles here as the face. Do, deca. Do means 2, deca means 10. This means 10 faces. The face is a pentagon. Icosahedron. This is 20-faced solid. Okay, and we have also the general formula to determine or the relation between the vertex, the number of face, and the number of edge of the solid. In this case, we have, in this case, this formula is called the Euler's formula. Okay, let's try this. What is the total surface area of an icosahedron if the length of each edge is 10 centimeter? Okay, we are to compute the total area of the solid. This is an icosahedron. Each face is a regular, or each face is an equilateral triangle. We may compute the area of each face, which is simply the area of an equilateral triangle of length 10. Again, the angle is equal to 60 because this is a regular or equilateral triangle. Now, we compute the total area by multiplying each triangle by, or by multiplying the area of the triangle by 20. Hence, an icosahedron, we have 866 as the total surface area. Okay, let's proceed to the sphere. This is our sphere, which is defined by the radius. This is the volume of the sphere, and this is the surface area of the sphere. Now, if we have this portion of solid on the sphere, an angle formed by an angle of theta. This solid is called the wedge. How do we compute the volume of the wedge? The volume of the wedge is simply a fraction of the volume of the sphere, meaning we can write its volume using the same formula as that of the sphere. But since this volume is only a fraction of that sphere, then we may write times that fraction. What fraction? It will depend on the angle theta. If the theta is 180 degrees, it means it is half of the sphere, because 180 is half of 360. If the angle is in degrees, then we retain the denominator to be equal to 360. Now, if we exclude the solid, we are only concerned of the area of this cut. Then we are referring to a lune, which is an area on the surface of that sphere. The volume, the area again, is a fraction of the area of the sphere, because this is simply a part of the sphere. But what part? Again, the fraction is still the same. It will depend on the total angle theta. If the theta is 180 degrees, it means that the lune is half of the sphere. Okay, now let us consider another object. Here is a sphere and we cut it on this side. What we get here is a segment. This one is a minor segment, this one is the major segment. Now, how do we compute the volume of the segment? The volume of the segment we computed using this formula. And if we are only concerned of the area of this solid, then we are referring to the zone. The area of the zone is defined by that formula. Okay, this one is called the sector. The solid that is bounded by the zone, and the cone is called the sector. To determine the volume of the solid, It is simply the sum of the volume of the segment and the volume of the cone. So we have the volume of the cone plus the volume of the segment. The total surface area is still the same, the area of the cone and the area of the segment. Let's try. What is the volume of a sphere whose surface area is 64 pi centimeters squared? We have a sphere, this is the volume, and that is the formula for the area. The volume is defined to be equal to, the area is defined to be equal to 64 pi. We are asked to compute the volume. Now, in the case of the volume, if we know the R, then we may define the volume. The R may be defined from the total surface area to be equal to 64 pi, which is 4 pi R squared. The only unknown here is R, then we can determine the value of R to be equal to 4. Now substituting R to our volume, we'll get our volume. A spherical wooden ball, 6 or 15 centimeter in diameter, sinks to a depth of 12 centimeter in a certain liquid. Determine the area exposed above the liquid. Here is our solid. This solid is submerged at a height of 12 or a depth of 12. How did we know that the upper or the okay? We know that this must be somewhere here on the other side of the hemisphere. It is because the diameter of the sphere is 15 and the height that is submerged is 12. It means it must be greater than the radius of the sphere, which is 7.5. Then the location of our zone must be somewhere here. Okay, this is our formula to compute for the area of that zone. We have 2 pi. The radius of the sphere is half of 15. And the h in this case, since the diameter is equal to 15 and the height that is submerged is 12, meaning the remaining length here of the sphere is equal to 15 less 12. Then we'll have the area to be equal to this value. Okay, we have another kind of solid which is look like this. This is a torus. It looks like a donut. Okay, on the side view, this is the section of the torus. Here, this is uh, the circle that generates the torus, and this is the radius of the torus, R. What is the volume of the solid? To determine the volume of the solid, it is not that difficult. We'll use the same definition for our solid, the upright solid. Let us consider that this torus has let us consider this circle here, which is found at the mid of the torus. If we cut the torus in that position, and then we force it to we force it such that we'll have an upright torus like this one. What we get or what we generate is an upright cylinder. As you may observe, we still have the same. This circular portion here is this line here. So what is now the volume of the torus? The volume of the torus may be computed as the volume of this cylinder. The volume of the cylinder, according to our previous formula, is area of the base. What is the area of the base now? The area of the base is equal to pi r squared, where r is the radius of the cross-section of the torus, times the height. But what is the height here? The height is simply the total length of this circle, which is the circumference of the torus. the circumference of the torus is equal to 2 pi r. So meaning, we may now compute the formula using the formula area of the base times height. I will just write that way in order to retain its meaning. This follows from the formula, or this formula follows from the principle of Pappus, the Pappus proposition. According to Pappus, the volume of a solid like the torus may be computed using this method. The area of the generating area times the total length of the circle, the total circumference of the circle. Okay, now let's proceed for the solids of revolution. Like for example, we have a parabola. If a parabola is revolved about its axis, what we get is a solid called paraboloid. The volume of the paraboloid is equal to this formula, 1/2 pi r square h. Take note that the volume of the paraboloid is just a fraction of the volume of the cylinder enclosing it. The volume of the cylinder is pi r square h, meaning if there is a cylinder enclosing a parabola or a paraboloid, the volume of that paraboloid is half of the volume of that cylinder. It's not difficult to recall. If you see a paraboloid, imagine a cylinder enclosing it. Half the volume of that cylinder is the volume of that paraboloid. Now, if we have an ellipse in this case, we have an ellipse, so let's say the semi-major axis is A, the semi-minor axis is B. In the case of ellipse, this has two axes. The bigger or the longer one is called the major, the shorter one is called the minor. Now, if this ellipse is revolved about one of its axes, it will generate a solid. What kind of solid? It may be called an oblate or a prolate spheroid. The ellipse is called oblate, or the spheroid that is generated is called oblate if after revolution the solid is an oblong solid. If it is not an oblong solid, then it is a prolate solid. It's an oblong if it is look like an oppo. If it is it is a prolate if it looks like a calabasa, no? So in the case of this solid, the volume is computed using this formula. 4/3 pi r square a. Now let us let's discuss this further. In the case of the sphere, the volume is equal to 4/3 pi r cubed. As you may observe from our spheroid that we have an equivalent r cubed here, b square and a. This is a cubic term. So, meaning the formula is not difficult to recall because you only have to recall the volume of the sphere. And you only provide a second power to the axis that generates circle. The axis that generates circle here is the semi-minor axis B. So that is why we have here B squared times A. As you may also observe that if the solid or if the ellipse is revolved about its minor axis, in this case is B, the solid that is generated is an oblong solid. That's why we call this an oblate solid. Now, if we revolve it about the major axis, the solid is not oblong. This is now spheroid. Sorry, prolate spheroid. And the formula will be similar except that the square or the power 2 is now on A. Okay, these are the solids of revolution. We have another solid here for this one, but this is not a solid of revolution. This is called ellipsoid. An ellipsoid is solid that has these properties. It has a radius in this direction, x. It has a radius in the y direction. It has a radius on the z direction. As you may observe, again, that the volume is similar to the volume of the sphere, 4/3 pi r cubed. But our r cube here, because we have different r's, we have a, b, and c. That's why we have this formula. If a, b, and c happen to be equal, like say equal to r, then the volume is the volume of the solid, which is of sphere, because this will become a sphere if all of the sides or the legs are equal. Okay, let's compute. A tank in the shape of a paraboloid is filled with water to a height of 5 meters, and the radius of the circular section at the water surface is 3 meters. Determine the volume of water inside the tank. Okay, we know if we have a paraboloid, then imagine of the cylinder. Half of the volume of the cylinder is the volume of that paraboloid. Now we have pi, the radius is equal to 3 square times 5. Then this is the volume of our paraboloid. Okay, for similar figures. Okay, here assuming I have a square with dimension x. If I double the length of the side, it means the new length of this side is equal to 2x, which may be written that way, x and another x. Obviously, the other sides will also increase. This is x, and this is x, then we have double the side to be equal to 2x. It also follows that the other side is also double because we are referring to similar figures. Now the question here is, if we double the side of an area, what will happen to the, if we double the length of an area, what will happen to the area? Did the area double? As we can see here, the area did not double. It is obvious that in this case, the area has quadrupled. This is our formula for the relation between the increase in the area with respect to the increase in the length. The increase in the area is equal to the square in the increase of the length. No, I'm sorry. The ratio, I mean, of the areas is equal to the square of the ratio of the lengths. In the case of our illustration, the ratio of the bigger area to the smaller area is equal to the ratio of their lengths. The bigger area is 2x. The corresponding length on the bigger is 2x. With respect to the original x, then we have 2 square is 4. As you can see, it is quadrupled. Similarly, if we have any other area, as long as we have a defined segment corresponding to the other segment here, then if we can monitor or trace the increase or the decrease in that segment, then we can also determine the increase or the decrease in the corresponding areas. Now for the volume, the same principle is applied. If the volume of the solid, if the segment of the solid is increased or decreased, then the ratio of their volumes is defined by this formula. The ratio of the final to the initial volume is equal to the cube of the ratio of their corresponding lengths or sides. Let's try this. Each side of a cube is doubled. By what percent is the volume of the cube increased? Okay, so we have here the ratio of the volume compared to the initial volume is equal to cube of the ratio of their corresponding segments or sides. Now, the corresponding sides has a ratio of 2. Because according to the statement, the length of the side has doubled, meaning if the previous side is x, the other side is twice of that length, meaning this is 2. Then the ratio of their volume is equal to 8. But the question is asking for the percent increase in the volume. Then first we need to determine that the final volume is 8 times of the initial volume. Then when we now compute the percent increase in the volume, the final minus the initial volume is the increase in the volume divided by the original volume is the percent increase in the original volume. Now substituting 8 times the initial volume as our final volume, then we can eliminate here the V and leaving only as 8 minus 1, which is equal to 7 or 700%.